Hi everyone, welcome to PharmaGrid. So today we will continue with the remaining pharmacokinetics related calculation series. Question number 6. Assuming complete absorption and an elimination half-life of 4 hours, how many milligram of a drug will remain in the body 12 hours after administering a 400 milligram dose? Assume linear pharmacokinetics, that is first order kinetics. Okay, so in these questions what all we know, elimination half-life of the drug is 4 hours and the initial dose is 400 milligram. Okay, and we need to calculate the amount of drug or the milligram of drug remaining in the body after 12 hours. After 12 hours means half-life is 4 hours. Okay, so 12 hours means 4 into 3, that is 3 half-lives. So what will be the drug remaining in the body after 3 half-lives? Okay, so we know that initial dose is 400 milligram. So in the first half-life means after 4 hours, this 400 milligram will become its half. That means 200 milligram. So in the first half-life, 400 milligram will become 200 milligram. Okay, that is one half, that is 200 milligram of the administered dose will be eliminated in 4 hours. That is in the first half-life. Then in the second half-life, now remaining is 200 milligram. Then of the remaining 200 milligram, one half, the half of 200 milligram is 100 milligram, will be eliminated in the second 4-hour period. Second 4-hour period means second half-life, or 4 plus 4, that is 8 hours. That is after 8 hours what will remaining? The remaining milligram of drug is 100 milligram. Okay, and in the next 4-hour span, next 4 hour means 8 plus 4, that is 12 hours. Then after 12 hours, this 100 milligram, remaining 100 milligram will become its half, that is half of 100 is 50 milligram. Okay, that is in the next 4-hour span, an additional 50 milligram of drug will be lost. Therefore, after 12 hours also known as, or also can be determined as 3 half-lives. Okay, so therefore after 3 half-lives or 12 hours, only 50 milligram of the drug remains. Okay, so this is the answer. If graphed as log drug remaining, that is in the y-axis, versus time in the x-axis, the data will appear as a straight line, okay, which shows first order kinetics. So here the correct answer is option C, that is 50 milligram. Next question. Estimate the plasma concentration of a drug when 50 milligram is given by intravenous bolus to a 140-pound patient if her volume of distribution is 1.6 liter per kilogram. Okay, so in this question we need to calculate the plasma concentration of the drug. So in this question, what all are the data given? The drug dose is given as 50 milligram and the weight is given in pounds, that is 140 pounds, and volume of distribution is given as 1.6 liter per kilogram. Okay, so we already know the equation for volume of distribution is equal to dose administered divided by initial plasma drug concentration. Okay, so from this equation we can calculate the plasma drug concentration. One can easily picture that the plasma concentration of the drug, which is denoted as Cp, will be equal to the amount of drug administered or absorbed divided by the volume of distribution. Volume of distribution means the body volume in which the drug is distributed. Okay, that is Cp. Cp is the plasma drug concentration, that is equal to dose administered divided by volume of distribution, or dose is equal to Cp into Vd. So in this problem we can do it step by step. In the step 1 we need to find out the weight of the patient in kilogram. Here it is given in pounds. Okay, we know that 1 kilogram is equal to 2.2 pounds. Okay, so in the first step, 140 pound into 1 kilogram divided by 2.2 pounds, that is equal to 64 kg. So we got the body weight of this particular patient as 64 kilogram. And the next step is to calculate the volume of distribution. Volume of distribution, it is given as 1.6 liter per kilogram, and we got the weight it as 64. So 1.6 into 64 is equal to 102 liter. Okay, so we got the volume of distribution as 102 liter. And the next step is we can substitute all these values in the equation. That is, dose is equal to Cp into Vd. Dose we know it is 50 milligram is equal to Cp. Cp is the plasma drug concentration which we need to find out, into volume of distribution, that is equal to 102 liter. So in the last step we can calculate the plasma drug concentration, which is equal to 50 milligram divided by 102, that is equal to 0.5 milligram per liter, which is the plasma concentration. So here the correct answer is option B, that is 0.5 milligram per liter. Next question. How many milligram of aminophylline should be given as a loading dose if a theophylline plasma level of 10 milligram per liter is desired in a 55-year-old male patient weighing 70 kilogram? His volume of distribution has been calculated to be 35 liters. Assume that aminophylline consists of 85% theophylline and 15% ethylene diamine. So in this question, we need to calculate the loading dose of aminophylline in milligram. So in order to calculate the loading dose, the equation is F into loading dose is equal to plasma concentration into volume of distribution, or loading dose is equal to plasma concentration into volume of distribution divided by F. F is the bioavailable fraction. So here plasma drug concentration is 10 milligram per liter and the volume of distribution is given as 35 liters, and here one clue is given. Okay, in order to calculate the bioavailable fraction, assume that aminophylline consists of 85% theophylline. So 85% means 85 divided by 100, that is equal to 0.85. Okay, so here the F value is 0.85. So substitute all these values in this equation. We will get the loading dose as, that is 10 milligram per liter, which is the plasma concentration, into 35 liter, which is the volume of distribution, divided by 0.85, which is the bioavailable fraction. So all substituting, we will get the answer as loading dose is equal to 412 milligram. F is the fraction of dose absorbed. So here the correct answer is option C, that is 412 milligram. Moving on to the next question. A drug has an elimination half-life of 3 hours and its apparent volume of distribution is 100 ml per kilogram. What is the total body renal clearance of this drug in a 70 kg male in terms of liters per hour? Okay, so in this question we need to calculate the total body renal clearance. Okay, so the volume of distribution is given as 100 ml per kilogram and the weight of the patient is given as 70 kg, and we need to calculate the clearance in terms of liters per hour. Okay, so since the volume of distribution is given as 100 ml per kilogram, that is in body weight, we need to convert this into liters. Okay, so 100 ml per kilogram into 70 kg, which is the body weight of the patient, that is equal to 7000 ml or 7 liters. So the clearance, the equation for calculating clearance is equal to Ke into Vd, where Ke is the elimination rate constant and Vd is the volume of distribution. And the equation to calculate Ke is equal to 0.693 divided by T half. T half means the half-life. So substituting all these values, we can calculate the clearance value. So clearance is equal to 0.693 divided by T half. T half is the half-life. Half-life is 3 hours into 7. 7 liters is the volume of distribution. Okay, by substituting all these values, we will get the value of clearance as 1.6 liter per hour. So here the correct answer is option B, that is 1.6 liter per hour is the total body renal clearance of this drug. Question number 10. If the half-life for the chemical degradation of kanamycin sulfate injection is 7.2 days, the time from preparation of the injection till 10% degradation occurs is. Assume first order kinetics. So in this question, we need to calculate the shelf life of kanamycin sulfate injection. So here, first we need to determine the K value. We know the equation to calculate the T half. T half or half-life is equal to 0.693 divided by K, where K is the rate constant. And from this equation, we can calculate the K value. K is equal to 0.693 divided by T half. T half is the half-life, which is given as 7.2 days. Okay, so 0.693 divided by 7.2 is equal to 0.09625. Okay, so we got the K value. And the next step is to determine the shelf life. Shelf life can be calculated by the following equation, that is T 90% is equal to 0.105 divided by K. K value we already got. So substitute K value in this equation. So we will get 0.105 divided by 0.09625, that is equal to 1.09 days, which will be approximately equal to 1.19 days. Okay, so here the correct answer is option D, that is 1.1 days. So with this question, we have completed today's calculation series. Thank you for watching this video. Have a great day.